Is everyone ready? Let's get ready for chemistry!
Coulomb's law says that the force of attraction is proportional to the charge of one thing times the charge of the second thing divided by the square of the distance between them. For a hydrogen atom, there's one proton, there's no neutrons, and there's one electron. So in the nucleus, there's one proton, and then around the nucleus, there's one electron. The size of the atom is the distance between the nucleus and the electron. Since this is a circle, this is the radius. For a hydrogen atom, the force of attraction is proportional to the charge of the first thing, the nucleus, the charge of the second thing, the electron, divided by the square of the distance between them. For helium, there's two protons, there's no one cares, and then there's two electrons. So then in the nucleus, there's two protons, there's no one cares, and there's two electrons. The distance here, the atomic radius, is the distance between the nucleus and the valence electrons. In helium's case, the charge of the nucleus is +2. The charge of the electron is still -1, divided by the square of the distance between them. Now, because the nucleus is twice as strong, the electrons are going to get pulled in more. So the atom of helium is going to be smaller than an atom of hydrogen. Helium, because it has more protons, is going to pull its valence electrons in more strongly, decreasing the size. Helium has 3 protons, helium has no one cares, and helium has 3 electrons. In the nucleus, there's 3 protons, there's no one cares about the number of neutrons, and then there's 3 electrons. Now the electrons are arranged in rings. Recall that the first energy level only holds a maximum of 2 electrons. The first 2 electrons go in the first energy level, and then the third electron goes in the second energy level. The radius, then, is the distance between the nucleus and the valence electrons. Only the valence electrons. The attractive force is going to be proportional to the charge of the nucleus, the charge of the electron, over the square of the distance between them. Unfortunately, this is wrong. We're not looking at the charge of the nucleus. We're not interested in the charge of the nucleus. We're interested in the effective nuclear charge. These electrons are screening this electron from being able to feel the full pull of the nucleus. The effective nuclear charge, then, is the number of protons minus the number of core electrons. In this case, the number of protons is 3, and there are 2 core electrons. So the effective nuclear charge is actually +1. Would this have the same atomic radius as a hydrogen atom? Don't they have the same equation here? But the difference is the lithium atom has valence electrons in the second energy level, where the hydrogen atom has valence electrons in the first energy level. So how are these related? The hydrogen atom is smaller than the lithium atom because the hydrogen atom has valence electrons in the first energy level and the lithium atom has valence electrons in the second energy level. So the more energy levels you add, the larger the atomic radius. A carbon atom has 6 protons in the nucleus, and also no one cares neutrons in the nucleus. The first 2 electrons go in the first energy level, and then 4 electrons go in the second energy level. The distance, the radius of the atom, is from the nucleus to the valence electrons. Carbon's going to have an effective nuclear charge of the number of protons minus the number of core electrons. The force of attraction is going to be proportional to the effective nuclear charge times the charge of the electron divided by the square of the distance between them. Since carbon has an effective nuclear charge of +4, we would expect the carbon atom to be smaller. The greater effective nuclear charge is going to make the force of attraction greater, which is going to make the carbon atom smaller than the lithium atom. Now, this is only true because the valence electrons for both are in the second energy level. So carbon's atomic radius would be less than lithium's atomic radius. This is the trend we see when we look at the atomic radius as it goes across a period. As the atomic radius in an energy level, we see that the radius decreases as you move across the period. This is because you're adding more protons to the nucleus, but you're not increasing the number of core electrons. So the Z effective nuclear charge, the ZF, is increasing as you move across a period. Same thing. As you move across a period, you would expect the atomic radius to decrease. However, as you move down the periodic table and you add new energy levels, the atomic radius gets progressively bigger because you're adding more energy levels. So moving down the periodic table is going to increase the size. Moving across the periodic table will decrease the size. Moving across the periodic table, the size decreases. Moving down the periodic table, the size increases. As you move across the periodic table, the effective nuclear charge increases. As you move down the periodic table, the energy level N increases. For the transition metals, it looks like the radius doesn't very much change. Scandium, for example, has 21 electrons. The 21st electron goes into the third energy level. The atomic radius is the distance between the nucleus and the valence electron. The valence electrons are in the fourth energy level. Titanium has 22 electrons. This is going into the third energy level. So the valence electrons are still in the fourth energy level. Vanadium has 23 electrons. This again is going into the third energy level. The 3D is in the third ring. So the valence electrons are in the fourth ring. So the distance from the nucleus to the valence electrons is the atomic radius. The effective nuclear charge for vanadium is the number of protons minus the number of core electrons Iron has 26 electrons. These electrons are going into the third energy level. The 3D sublevel is in the third ring. The effective nuclear charge for iron is 26 protons minus the number of core electrons is still +2. So all of the transition metals are all going to have something that looks like this. Because as you add an extra proton to the nucleus, you're also adding a core electron. So the effective nuclear charge is staying constant across the row. So for the transition metals, the effective nuclear charge is staying the same, and so it ends up continuing to be very similar. Now there are some slight differences, but for the most part what we would conclude is that transition metals have a fairly constant atomic radius. So moving across the periodic table, the radius decreases. Because we're adding protons to the nucleus, we're increasing the effective nuclear charge. As we move down the periodic table, the atomic radius increases because we're increasing the number of energy levels. So we're increasing the distance from the nucleus to the valence electrons. The calcium atom has 20 protons and 20 electrons. The radius would be from the nucleus to the outside electrons. The effective nuclear charge would be +2. The calcium ion has a +2 charge. This means it's lost 2 electrons. Which electrons did it lose? The valence electrons, the electrons from the 4th energy level. Now that those are gone, the atomic radius is between the nucleus and the electrons that are now the valence electrons in the 3rd energy level. Now there's only 10 core electrons. So the effective nuclear charge is +10. Because there's a greater effective nuclear charge, the outside electrons can be pulled closer to the nucleus. But there's a more significant difference between the two. The valence electrons in the calcium atom are in the 4th energy level. The valence electrons in the calcium ion are in the 3rd energy level. So the calcium ion is much, much smaller than the calcium atom because it's an entire energy level smaller. Oxygen has 8 protons and 8 electrons, and the radius is from the nucleus to the electrons. The effective nuclear charge for an oxygen atom +6. The oxide ion has an extra 2 electrons. The effective nuclear charge is +6. The valence electrons here are in the 2nd energy level, and the valence electrons here are in the 2nd energy level. So at first glance, it looks like there's no difference between the two. And you might be thinking that the anion would have the same atomic radius that the parent atom would have, but this is not true. And that's because we've only been talking about one force in this atom. So far, we've only been talking about the attractive force between the nucleus and the valence electrons. But that's not the only force involved here. There's also the repulsive force between the electrons around the same atom. These electrons are going to be trying to repel each other to get as far away from each other as possible because like charges repel. Adding more electrons to the atom means there's more electrons trying to get away from each other. And for a circle, the only way that you can get them further away from each other is to make the circle bigger. So the oxygen ion, oxide, is larger than the parent oxygen atom because there's more electrons repelling each other around the nucleus. Cations always get smaller than their parent atoms. Anions always get larger than their parent atoms.